Hello folks, I welcome you all to JK Tech Solution YouTube channel. In this video, I am going to walk you through the design of circular microstrip patch antenna at 3 GHz. To design the circular microstrip patch antenna, now let us discuss the feeding techniques. As you can see on the screen, there are two types of feeding techniques. The first one is contacting feed and the second one is non-contacting feed. In contacting feed, there are two subdivisions. Their first one is microstrip line feed and coaxial feed. In non-contacting feed, it is further subdivided into proximity feed and aperture coupled feed. In contacting feed, now we are going to design the circular microstrip patch antenna with the coaxial feed. As you can see on the screen, uh, about the design specifications of the circular microstrip patch antenna at 3 GHz. So first, as you can see here, the resonance frequency which is equal to 3 gigahertz. Then the substrate that we are going to use for designing the circular microstrip patch antenna is FR4 epoxy, whose relative permittivity epsilon r is 4.4. Then the height of the substrate is 1.6 millimeter. Then finally, as we already discussed, the feeding technique that we are going to use for this circular microstrip patch antenna is coaxial probe feed. Then next, we need to calculate the radius of the circular patch. So initially, in order to calculate the radius of circular patch, we need to find the parameter f. To find the parameter f, we need to know the resonant frequency and relative permittivity. The resonant frequency is 3 gigahertz and the relative permittivity is 4.4. Now we are substituting those values in equation 1. After substituting the design values, we get the f value as 1.395 into 10 to the power minus 2 meter in the equation number 2. The next, we are calculating the actual radius of circular patch, whose formula is given by A equal to f divided by square root of 1 plus 2h. As you can see here the h is nothing but the height of the substrate. Then epsilon r is nothing but the relative permittivity. Then here we need to substitute the f value. After substituting all these values, we get the a value nearly equal to 13.4 millimeter in equation number 4. Next, we are calculating the ground plane dimensions. For the ground plane, length and width must be greater than or equal to 6 times the height of the substrate, and it must be and we need to add it with 2 times the radius of circular patch. Here, as you can see here clearly, this is what a constraint that we have, 6h plus 2a. The length and width must be greater than or equal to 6h plus 2a. For practical implementation, we consider the ground plane size, that is length and width, is equal to 61 millimeter after optimization. Next, we are calculating the feed point location. To calculate the feed point location, we have the formula which is equal to 0.3a. After substituting the a value is 13.4 millimeter. We get 4 millimeter as a feed point location from the center of the circular patch. It was provided in equation number 8. So here is the expected performance parameters that we expect after simulation. That is, frequency is 3 gigahertz, and these are all the parameters that we expect after simulation. Now let us start the simulation part. Now open ANSYS HFSS. I've already opened and set up the ANSYS HFSS software. Now we start our design process from ground. Now just click the rectangle and draw here. Here first rename the rectangle to ground. Then give apply. Okay. We need to plug in the dimensions for the ground. As we already discussed, the 61 millimeter as X and Y size. Click apply, then OK. Give fit all, as you can see here clearly. Now next we need to draw the substrate. Using box we have drawn the substrate. Now let us assign the dimensions, that is 61 millimeter. Then 61 millimeter. The height of the substrate is 1.6 millimeter. Click apply. OK. Now rename the box to substrate. Now we need to assign the material to substrate. I'm assigning the material to substrate as FR4 epoxy. OK. Then you have to click on apply. OK. Then we need to draw the circular patch. To draw the circular patch, you need to move the cursor to the center point. Then you need to draw the circle for the patch. Rename the circle 1 to patch. Then click on apply. OK. So for this patch we need to assign the dimensions whose radius is 13.4 millimeter. Click on apply. OK. Now as you can see here, the view of our antenna clearly. Top view where you have the patch, and then the bottom view you can see here the ground plane. Now our next step is to give the coaxial feed to this circular patch. To provide the coaxial feed, now let us cut the ground plane. So let me change the orientation and let me draw the circle to cut the ground plane. As I already stated it, there must be 4 to 5 mm between 4 to 5 mm distance between the center of the circular patch and the edge of the patch. Now as I give the center point as 34.9 comma 30.5 comma 0 mm, then the radius is about 1.8. Click on apply. OK. So here 30.5, you have to give subtract minus symbol, then you can view clearly here. Now as you can see here the ground cut. So rename the circle 1 to GND cut. Then give on apply. OK. So for your better understanding, what I am going to do right now here is that instead of 34.9 in the ground cut, let me plug in the as x1, then I add the value as, then I plug in the value as 34.9. It would be easier for you. Otherwise we need to assign value again and again, it will be somewhat complicated. Then let me give it to x2. I give the value as 30.5. The unit is meter. Give OK. Now give apply, then OK. Let me give here also the meter 34. So now you can see here the clearly the ground cut part. Okay, now we need to subtract the ground from the ground cut part. So in the blank part ground should be there, and the tools part the GND cut must be there. Click OK. Now as you can see here the hole for the coaxial feed. Now the next step is to draw the feed out. So to draw the feed out, let me have the orientation in trimetric plane. So initially I draw the cylinder. So I rename the cylinder to feed out, and for the feed out let me assign the material as PEC. Then give OK, apply, then OK. Let us assign the dimensions to the feed out. The radius is about 1.8. Then the center position is x1 comma minus x2 comma 0. So here x1 x2 are variables which was assigned earlier. Okay, as you can see here the feed out, the height must be negative, then only you can able to get minus 5. Click apply. OK. Now as you can see here the feed out below the ground plane. The next we are going to give the flinch. Let me give proper orientation. Now for the blinch also we need to draw a cylinder and rename this cylinder to blinch. So here blinch is nothing but the part between the outer cylinder, inner cylinder is outer feed and the inner feed. Okay, that between the outer feed and inner feed a blinch part is present. So for that I'm going to assign the dimensions. Similar position I'm going to assign, that is x1 comma minus x2 comma 0. Then the radius is about 1.67. Then the height is minus 5. Then give apply. OK. Now as you can see here clearly the flinch part, then the feed out, both also you can see here clearly. Our next step is to give the feed in. For that I let me create the cylinder and rename the cylinder 1 to feed in. Then I assign the material as PEC, give apply, then OK. So now we need to plug in the dimensions to the feed in. The radius is about 0.5. Then the center position is x1 comma minus x2 comma 0. Here the height is minus 5. Then click apply, then OK. So now as you can see here the feed in also clearly, you can see here clearly feed in, feed out. Here the blinch part is present. I think now it is clear for you. Now you can Observe the patch on the top of the substrate. Now we are going to draw the feed patch. For that, let me draw another cylinder and rename that cylinder to feed patch. We say it as probe also, feed patch probe. Let me give apply. Okay. Now for this, let me give the dimensions. Center position is similar, that is x1 comma minus x2 comma 0. Then the radius is about 0.5. Then the height is 1.6 millimeter. You apply. Okay. Now as you can see here, the feed patch probe, feed in also you can see, feed out, then blend spot. So all the pots are visible. So for this feed patch probe, let me assign the material as PEC. Then give apply, then OK. Now let us assign the perfect E to the ground plane. Let me click on assign excitation, assign boundary, perfect E, perfect E1. Then to the patch also we need to assign the perfect E, assign boundary, perfect E. So now we have assigned the boundaries to both patch and then the ground. Our next step is to assign the port. To assign the port, we need to draw the circle. Then only we can able to assign the port through the coaxial feed. Let me draw the circle here. Now let me check the dimensions here. So here also same x1 comma minus x2 comma 0. Here the radius is about 1.8. Then give apply, then OK. Here the height is minus 5. X1 comma x2 comma minus 5 will come here. Click apply. OK. Now as you can see here the circle clearly, that is x1 comma x2 comma minus 5 with the radius. Now let me give the proper orientation. Now as you can see here the circle one clearly. Now let me rename this circle to the port. The port. Then give apply, then OK. So now to this port we are going to assign the excitation. So now I'm going to assign excitation port, terminal lumped port, use port object name, then give OK. Now as you can see here clearly we have assigned the excitation to the port, that is lumped port we have assigned. The next step we need to do here is to create a open region, and we are designing for 3 gigahertz frequency. Click OK. So now we have created a radiating surface. Give it all. The next we need to assign the analysis setup, add solution setup, advanced. The frequency is 3 gigahertz. Then give OK, give OK. So now let us validate our design. Now to click on validation check. Here our design satisfies the validation check. So we can move on to the simulation. So to simulate, click HFSS, then analyze all. Now the simulation have started. It will take few minutes for simulation. Let us wait for few minutes. Now as you can see here, the simulation part is completed. Now let us validate the results. Now let me show the results. To see the S parameter, you need to click on HFSS. Results. Create terminal solution data report. Rectangular plot. First we take the S parameter. Click on new report. As you can see here, we got the frequency exactly at 3 gigahertz with minus 25.3659 as return loss. Then next, you need to calculate the bandwidth. To calculate the bandwidth, you need to click on marker, add Y marker. At minus 10 dB, we calculate the. So as you can see here, the values. Okay, so we need to subtract the upper cut and lower cutoff frequencies. Then we can able to find the bandwidth. The next, we can calculate the VSWR results. Create terminal solution data report, rectangular plot. Here you need to click on terminal VSWR. dB function should be, click on new report. At 3 gigahertz, we got the VSWR value which is less than 1. The next we need to take the gain plot, HFSS, create Fairfield's report, 3D polar plot. Gain total must be in dB. Click new report. As you can see here, the gain we have obtained is about 4 dB. 4.03 maximum gain we got is 4.03. The next we take here results, create far fields report, radiation pattern. Now let us check the radiation pattern. To check the radiation, we need to change from theta to phi. Then the families, you need to click theta, select frequencies to 90 degree. Click, then click new report. Now as you can see here, the broadside radiation pattern have been verified. So we have verified all the parameters starting from S parameter, terminal VSWR parameter, then gain plot, then the radiation pattern. Now let us find the bandwidth. Here as you can see here, the bandwidth formula is F2 minus F1. We substitute the values that have been taken from the S parameter plot at minus 10 dB, and we get the bandwidth as 80 megahertz. And here we calculate the fractional bandwidth. So in which the center frequency formula Fc is equal to F1 plus F2 by 2. We substitute the 2.98 is lower cutoff and upper cutoff 3.06, and we get the center frequency is 3.02 gigahertz, and the fractional bandwidth is equal to bandwidth divided by FC. Here the bandwidth is 0.08 divided by FC is 3.02. In terms of gigahertz we are writing. So here the bandwidth is in 80 megahertz. We are for calculating the fractional bandwidth, we convert the megahertz to gigahertz and we get 0.08 divided by 3.02. So finally we get 2.65 percentage as fractional bandwidth. Thank you so much for patiently watching this video. I hope you to see you again on next video. Thank you. Have a nice day.